We're going to look at some bases in this section. We'll start with strong bases, and there's sort of a general formula for it. So we got our OH molecule, and it's strong, so we have a straight arrow, and it's making our OH. Now you got to remember that with this one, we have a 1-to-1 ratio of our reactants to each one of our products. So if we start with 0.2 molar, that means that each of our products also has that same molarity. That's not always the case. So for instance, if we had a base that had 3 hydroxides in it, of course we put a 3 over here, that means that we now have a 1-to-3 ratio. So if we start with a 0.2 molar here, sure, this one's a 0.2 molar still because it's a 1-to-1 ratio, but we would have to triple that molarity. So that times your 0.2 gives you 0.6. And technically in this case, you've sort of found the pOH. And you can adjust that to pH by just taking 14 and subtracting that value. So taking a look at a question here, we want to determine the H plus, OH minus, and pH and pOH of a solution of zinc hydroxide with a concentration of 0.015 molar. So there is our equation, and just like I mentioned in the previous slide, that when we get to the hydroxide, we have a 2 in front of it, so it means we need to double our molarity from here, so it doubles to that value. So we can go ahead and take the pH of this number here, which is 0.3, and we get a pH of 0.5. And now we got to do some rationing though. This is a base. We know bases have pHs of 7 to 14. So technically we haven't found the pH. We've found the pOH. So if we want to go ahead and calculate the pH, then it's just really going to be some subtracting here, moving around of the values. And there is our pH value, 13.47. That falls into the basic range. So if we want to do our concentration here, we've got our Kw. We can rearrange it for Ka. Another question does say find the hydroxide concentration. We actually sort of did that right there. I didn't mention it. But just proceeding here, we've got our known value of Kw, and we're taking our 0.03, putting it there, and that will be our Ka value for this question. So I bet if you took the negative log of this number, you would probably get our 0.53 value. Morphine is a pain medication of the opiate family that is found naturally in several plants and animals, including humans. It acts directly on the central nervous system to decrease the feeling of pain. To determine the pH of a solution with a concentration of 0.01 molar and a Kb of 7.5 times 10 to the minus 7. This one we can jump directly into an ice chart. So there's our equation. Now this is basic. And so what's happened here is we've taken a hydrogen from here and put it over to that side. So you'll see we've gone up to 20, and now we have our OH value here. So there's our ice chart. There is our initial concentration. There is our change in concentration, and there is our equilibrium. So putting this all together, there's our Kb expression. We can get rid of the water because it's not contributing. And we can sub things in, and then this is the case where you can do the 100 rule, but I don't know if you've noticed that this value here tends to get disregarded always. So we're just going to adjust our statement by getting rid of that, and then it's from cross multiplying, and now we take the square root of both sides, we get that value, and now with this we can go ahead and figure out the pH and pOH. So there's our equation. We're taking the negative log, and we've got our pOH. And again, it's a base. So we can subtract, and we can get our pH value. And I think that makes sense too for the pH of this because it's a base. It's in the basic range.